Welcome back everyone. In this lecture we will continue the classification of admissible subsets of any Euclidean space. So, let me begin with recalling the definition of admissible sets. So, you have the Euclidean space C that is fixed, and then let us assume the dimension of that Euclidean space is L, and a subset, finite subset of unit vectors of capital E is said to be admissible. So, we have the following conditions that should be satisfied by these vectors. So, if it satisfies the following conditions. So, what are they? The very first condition, they should be linearly independent plus they are all unit vectors. So, the second condition, if you take inner product epsilon ij, that should be non-positive for all I not equal to j. That means they have obtuse angle between them. So, the third condition, it is about the like Cartan numbers. So, 4 times epsilon I epsilon j, the square it has to be either 0, 1, 2 or 3 for all I not equal to j. So, these are all the 4 conditions. So, now then what we did, we defined a Cox-Stuck graph associated with this capital A, which we denoted by G of A. So, what is G of A? The vertices of G of A are nothing but this epsilon 1 etcetera epsilon n, and then for I not equal to j, you draw exactly between epsilon I epsilon j exactly 4 times epsilon I epsilon j square number of edges between these two vectors epsilon I epsilon j or the vertices. So, note that this number can be at most 3. So, then you may have exactly either 1, 2 or 3. Okay. So, what we observed so far, we observed that any subset of an admissible set must be admissible, and if you count the number of pairs of vertices, which you count it as unordered pair in G of A such that they are connected by at least one edge. So, that number must be strictly less than L, that is what we say. We also saw that using that G of A cannot have any cycle. So, then later using that we saw that if you take one vertex inside G of A, and then at most 3 edges can originate from that vertex. So, those are all things we proved. Okay. So, let me recall any subset of an admissible set, subset of an admissible set must be admissible. So, this is easy to see. So, then you count the number of pairs, okay, basically I j such that epsilon I epsilon j is non-zero. So, this has to be less than n. The third point, G of A has no cycle. So, that is immediate corollary of this 2. So, let us label them 1, 2 and 3. So, this just follows from 2. The fourth condition, if we take some vertex epsilon, okay, then at most 3 edges can originate from that vertex. Okay. So, no more than 3 edges can originate at a vertex of G of A. And using this we saw that if G contains this triple H, then G of A must be this particular graph, the Coxeter graph of G2. If G of A connected and contains triple H. Okay, so these things we have already proved in the last class. So now we will continue our analysis and then see what are all the other possibilities that we can have. So here is the next observation. So suppose assume that G of A actually contains some simple path. Okay. So let us say this is the simple path epsilon 1 to epsilon k. So this is there inside G of A. Okay. So then what we want to do, we want to actually shrink this path to a point. Okay. So then we get another graph. Okay. So that graph we want to climb that will be again admissible graph of that will be a Coxeter graph of some admissible set. So for example, if we have something like this, so then for example, if this is actually a simple path inside this graph, so then you can actually string this and then make it a point. So then you can actually have something like this. So we want to climb, this is again Coxeter graph of some admissible set. Okay, so how one does that? So basically A contains this epsilon 1 etc. epsilon k. So those are all distinct vectors. So since this is a simple graph, you can see that epsilon I plus 1. So this 4 times this square must be 1. So that implies twice epsilon I plus 1 must be minus 1, because epsilon I plus 1 must be negative, and then this square root of that is minus 1, and this is true for all I less than k less than or equal to 1. All other inner products will be 0. Okay, so that is what you get it from this simple graph. So now what we do, we just take this A difference epsilon 1 etc. epsilon k, and then we just union this one single vector which we call it epsilon, which is just summation epsilon I ranging from k. And then we claim that this new set which we call it A of epsilon. So this is an admissible set. So this is admissible set, and it is easy to see this set actually, the graph of this set satisfies the property that we claimed. Okay, so this is the claim. Okay, so how one goes about it? So for to prove this is an admissible, because we added this one more vector by removing all this epsilon etc. epsilon k. So we have to verify all the properties. So in particularly we need to verify. So we need to verify the following things. So what we need to verify, this epsilon, so that should be unique vector. That is one thing we need to verify, and all elements of this A of epsilon that must be linearly independent. So that is something we need to verify, and this is obvious because A itself consisting of linearly independent element, and you have removed this epsilon 1 etc. epsilon k, and then added one element from the span of epsilon I. So that will make again simply linearly independent. So this is fine. So only we need to verify this. So the second thing, whenever you take this 4 times epsilon and then some eta square, so this should be either 0, 1, 2, 3 for any eta coming from A of epsilon. So, this is something we need to verify. Okay, let us see, let us verify one by one. So, let us compute epsilon epsilon and then see what we get. So, from the definition you can see that the epsilon epsilon, which is summation epsilon I ranging from 1 to k. So, epsilon epsilon will be exactly equal to k plus twice summation epsilon I epsilon j, where I less than j, I j runs over the pairs I j such that the inner product epsilon I epsilon j is non-zero, which is exactly equal to k plus summation twice epsilon I plus 1 I ranging from 1 to k minus 1. So, then you can see that epsilon epsilon is exactly k plus minus k minus 1. So, which is exactly 1. So, that means epsilon is a unit vector. So, that is not hard. So, now you take any eta. So, that is from this A of epsilon. So, that means A difference epsilon 1 etcetera epsilon k. So, because if eta is epsilon, there is nothing there. So, you just take it from this A difference epsilon etcetera epsilon k. So, now you can see that this eta that can be connected to at most one of this epsilon etcetera epsilon k. That is because this eta is actually coming from somewhere outside. So, this is epsilon etcetera epsilon k, and then this eta is somewhere here. If this eta connects with two of them, then that will make a cycle. Okay. So, that is forbidden, because we already observed that G of A cannot have any cycle. Okay. So, that means this can be connected with at most one epsilon I. So, in particularly you can see that this eta epsilon, so that can be either 0 or this eta epsilon is exactly equal to eta epsilon I. So, in both cases you can see that 4 times eta epsilon square. So, that is going to be just 0, 1, 2 or 3, because in this case there is nothing to prove, but in this case it is just going to be 4 times eta epsilon I square, which is either 0, 1, 2, 3. So, that proves that A of epsilon that we constructed is an admissible set, and it is not hard to see, because if you take any eta that is from outside. So, that eta either it has an edge between one of epsilon i's or not. So, in either case when you shrink it, it will have either edge from eta, eta will have edge between epsilon or epsilon I. So, by shrinking you get edge from epsilon to eta. Okay. So, in the new graph you will have edge if and only if you have edge in the old graph. So, that way you can see that the graph of A of epsilon is obtained by shrinking the simple path to a point. So, this is indeed very interesting observation. So, basically it restricts many things actually, kind of what I want to say, like, so this puts lots of restriction on G of A, and then you can observe that G of A cannot contain subgraph of the following forms. Okay. So, this is our 7th observation. So, you can prove that easily G of A contains no subgraph of the following forms. So, what are they? The very first one is something like this. You have double edge, and then you go all the way, and then you get again one double edge. So, this is a path you can see. So, then you can see that from this, by shrinking this path, you can actually take it from here also, like from here you can take all the way here, and then you can see this is a simple path. So, by shrinking it you can see that you get something like this. But we already seen that if you have a vertex in an admissible set, okay, and then Coxeter graph of that. If you have a vertex, then no more than 3 edges can originate from that vertex. But you can see that by shrinking this, you got again admissible set for which this vertex has 4 edges originating there. So, that is not possible at all. So, this is not possible. So, this kind of things you can't have. Similarly, you can see that you can't have something like this. So, double edge and then you go all the way and then you take this branch. So, then from this you can see if you shrink this part, then you get something like this. You have double edge and then you have this branch. So, then this vertex has 4 edges originated from that. So, again that is not possible. Similarly, you take 2 branches, okay, from inside your G of A, then again you restrict to this particular subset, it will be admissible set. So, it is Coxeter graph of an admissible set. So, then you take this particular simple graph as before and then just shrink it. So, then you get something like this, and again this vertex has 4 edges meeting it. So, that is again not possible. So, these things are not allowed at all. So, all these 3 are not allowed. Okay. So, that again puts lots of restriction on your graph. Okay. So, now more or less we are ready to prove what we want. So, from this you can immediately conclude that if you start with any connected graph, that is connected Coxeter graph, let us say G of A of an admissible set. So, then that must have the following forms, okay, has the one of the following forms. So, what they are? So, either it can be just simple path. So, when this case happens, if it contains no multiple edges and no branches, okay. So, this is the first case, no multiple edges and then no branches. So, in this case you can have something like this. So, this is just a simple path. So, this is the Coxeter graph of type A. So, this is the Coxeter graph of type A. So, the next case, so G may contain multiple edge, let us say it contains triple edge. G contains, that is G of A contains connected, okay, that is already assumed. G of A contains a triple edges. So, then we already observed that in this case we have G of A must be of the form just this type G2. So, this is the Coxeter graph of type G2. Okay, these 2 cases are fine. So, now what are all the options? Now, it can have multiple edges. So, now it cannot have triple edges. So, it can have only double edges. So, double edges and branches. Okay. So, in case if it has double edge, okay, let us say G contains and double edges. Okay. So, that means something like this is there inside the graph of G of A. But now go back to our earlier observation, you can see that if it contains double edge, then there should not be another double edge. Okay, then you can take this particular path that connecting them, and that will actually will give you like subgraph of this form. So, that tells you that if it has double edge, then it should not have another double edge. So, now if it has double edge, then again it cannot have a branch. If it has a branch, you can have a subgraph of this form. So, that more or less forces that actually forces if G contains some double edges. So, then it has to be of the form something like this. There is no other option. So, you label them like epsilon 1, epsilon 2, etc., epsilon p minus 1, epsilon p, eta q, and then eta q minus 1, eta 2, eta 1. So, this is the only possibility. For example, it includes F4, Bn and Cn. Okay. So, these two are equal as Coxeter graph. So, again later we will see again some restriction will be there in P and Q. Okay. From that we will conclude this, but this is clear, because if there is one double edge like this, then we cannot have another double edge and any branch. So, that forces that this is the only possibility. So, now let us assume there is no double edge and triple edge is already overruled. Then let us say G contains a branch. So, branch means something goes like this, okay? That is what branch. So, now you can see that if it has branch, then it cannot have multiple branches, because if it has two branches, so then you can see that you will have a graph something like this, subgraph something like this. So, that forbids actually you can't have two branches. So, at most one branch will be there. So, since it has only one branch, so then the possibility will be something like this. You will have a branch like this, and then you can have something like here, and then something like this here. So, this branch node you call it xi, and all these other nodes you can label them like epsilon 1 to epsilon 2, and then xi r minus 1, xi 2, xi 1, and then eta q minus 1, eta 2, eta 1. Okay. So, now these are all the only possibilities, and we have listed all of them. So, if you start with the connected graph, it can if it does not have multiple edge and branch, then this is the only possibility. If it contains triple edge, then this is the only possibility. If it contains double edge, then this is the only possibility, and if it does not have multiple edges, then but contains branch, then this is the only possibility, and this exhausts all the things that we have already. So, now from this what we are going to do, we will take graphs of this form and then see whether more restrictions are there or not. For example, if you take a simple graph like this, which is a Coxeter graph of type A, there is we can't do anything more, then we can ignore this, and similarly this G2 is also nothing can be done. So, that also we will ignore. So, now we will take let us say this particular type of graph and then see. So, this particular type and then see what we can do. So, that is what we are going to do now. So, this is number 9. So, the only connected graph G of A that contains double edge. So, that they are actually the Coxeter graphs of Bn, which is also same as the Coxeter graph of Cn and F4. So, this is the claim. So, the only connected G of A, that is graph of this admissible set, that contains double edge. So, or the Coxeter graph of Bn, which is same as Cn and F4. Okay. So, how one proves this? So, here is the trick. We consider two particular elements and then compute inner product between them as before. Again the inner product will contain all the restrictions that we need. Okay. We need to basically compute the number of edges that are possible. Okay. So, that means if you take this inner product, that should capture the number of edges between that are concerned here. So, that is why we take this particular elements. Okay. Let us take this epsilon to be summation I epsilon I, and then you take this eta to be summation I eta I. So, now you see that if you consider inner product epsilon 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 eta eta eta. So, then all the inner product that we are interested in, it will all appear there. So, note that from the graph. So, the graph looks something like this, where epsilon p minus 1 eta q eta 2 eta 1, this is the labeling that we had. Okay. So, now you can see that epsilon I plus 1 as before, the twice of that will be minus 1. Similarly, twice of eta I plus 1 will be minus 1. Now, not only that, if you take 4 times epsilon p eta q square, so that must be 2. So, this is what you read it from the graph. All other inner products will be 0. Okay. So, now it is not hard to compute what will be this epsilon epsilon. Okay. I will leave it to you to check. So, this is easy to check. So, this epsilon epsilon, if you compute, it is exactly p into p plus 1 by 2. So, this just you get it from this information, that twice epsilon I plus 1 is exactly minus 1. So, now if you go back, so this is from I ranging from 1 to p, and then this is I ranging from 1 to q. So, that is why you get this. Similarly, if you compute eta, so this is also going to give you q into q plus 1 by 2. So, these computations are easy to do. So, now if you go back and then compute what is epsilon eta square. So, that you can see that because epsilon eta except epsilon p eta q, they are the not orthogonal elements. So, then you can easily see that this is going to be exactly p square q square epsilon p and then eta q whole square. So, which is going to be exactly because epsilon p eta q square is nothing but exactly equal to 1 by 2. So, if you put that 1 by 2 here, it is going to be p square q square divided by 2. So, that is what you get. So, now you can use Cauchy-Schwarz inequality. So, Cauchy-Schwarz inequality says if you compute epsilon eta square, that has to be strictly less than the inner product epsilon epsilon and eta. So, that is because epsilon eta both are linearly independent vectors, okay, as epsilon and eta are linearly independent, because epsilon is sum of epsilon i's and eta is sum of eta i's, okay, the multiple of eta i's. So, both are like linearly disjoint linearly independent sets. Okay. So, it lies inside two different spaces. So, it must be linearly independent. So, this must be true from Cauchy-Schwarz. So, we repeatedly use Cauchy-Schwarz because basically in the inner products are involved here. So, Cauchy-Schwarz is actually puts lots of restriction between these inner products, that is what we are doing. Now, you can see that this is going to be exactly gives us p square q square divided by 2 is less than p into p plus 1 by 2 times q into q plus 1 by 2. Now, if you simplify, then you can see that this is going to give you exactly p minus 1 times q minus 1 is less than 2. So, I will leave it you to check this. This is again plain computation, nothing else. So, now what you can get from this inequality, p minus 1 times q minus 1 is less than 2. This is what there, p and q are integers. Okay. So, we have assumed p and q are actually greater than or equal to 1, because so not necessarily p could be p and q should be greater than or equal to 1. So, p q are non positive integers. sorry, non-negative integers, positive integers. Okay. So, now you can see that p minus 1 times q minus 1 is less than 2. Okay. For example, p could be 1. If p is 1, this inequality is true. So, q can be just arbitrary, and if q is 1, so then p will be arbitrary. But what you get in this case, if p is 1, then you get something like this, double H and then just this, and if q is 1, you get something like this, and both are isomorphic. Okay. Basically, you can see that they are just isomorphic. Now, what is other choice? Other choice is p can be 2 and then q can be 2. Okay. This is the other choice. In this case, again this will be satisfied, but in this case you can see that you get F4. So, there is no other options are possible, because if p is greater than or equal to, for all other tuples p, q positive integers, this inequality will not be satisfied. So, that is easy to check. So, now what we proved in this case, we are getting either Bn or F4. So, that is what we proved. So, now similarly, what one can do, one can take this particular type and then using similar arguments, you can actually conclude the only connected G of A of this type. So, let us say this is the fourth one, okay, because the first one is type capital A and second one is type G 2, the third one is either F4 or BC that we have seen, the fourth one we want to understand. So, the fourth one we get only the Cox-Stuck graphs of either Dn or E6, E7 or E8. Again we will do like similar analysis. Okay. Maybe I will leave all the computation to you, I will just do the I will just tell you how it is proved. So, again you take epsilon to be summation I epsilon I and eta to be summation I eta I, and then xi to be summation I epsilon I. So, you can see that all of them are mutually orthogonal and they are linearly independent vectors. So, recall how the graph is there. So, this is the branching node that we call it xi and all other things are here. For example, this is epsilon p minus 1 to epsilon 1 and this is xi r minus 1 to xi 1 eta q minus 1 to eta 1. This is the labeling that we have. Okay. So, that means you can see that if you remove this epsilon, so then all others are actually epsilon is combination of this, eta is combination of this and xi is a combination of this. So, they are all orthogonal to each other, in particularly they are linearly independent, and xi is not in the span of all these three vectors epsilon, eta and xi. So, now you can use the earlier arguments. For example, you can consider the span of these four vectors xi, epsilon, eta and then xi. So, this is going to be 4-dimensional space, and since this is orthonormal subset, so you can extend it to be orthonormal basis. Then you can take this to be span xi naught, epsilon, eta, xi. So, then you can see that you can write xi as xi naught plus xi epsilon plus xi eta plus xi. So, note that xi naught must be non-zero because xi is not in the span of epsilon eta xi. So, this is again like it is exactly the argument that we gave earlier. So, since this xi is unit vector, this is going to put lots of restriction on the inner product. So, this is unit vector that says that xi square must plus xi epsilon square plus xi eta square plus xi square. So, this sum must be 1. So, then this implies that if you take this subsum, so that must be at most 1. What is this subsum? So, this subsum is nothing but just the squares, cosine squares, okay, between the angles between xi and epsilon, eta and xi. Okay. So, this is exactly cosine square theta 1 plus cosine square theta 2 plus cosine square theta 3, where theta I 1, theta 2, theta 3. So, these are the angles between xi and epsilon, eta, xi respectively. So, this geometric constraint is actually very much one can use and then conclude what we want. Okay. So, I will leave the all calculations. So, you can check whatever I am claiming. So, it is easy to see that from again using earlier calculations, this epsilon epsilon will be p into p minus 2 and then eta eta will be exactly q into q minus 1 by 2 and then the xi xi will be r into r minus 1 by 2. So, now if you compute this cosine square theta 1 using the cosine formula. So, then this is going to be epsilon xi square divided by epsilon epsilon times xi xi. So, now xi xi is unit. So, then you can see that this is going to be exactly equal to p minus 1 square and then xi p minus 1 times epsilon p minus 1 times xi square, because all other vectors will be orthogonal to xi. So, then this is what you are getting, and if you simplify this, you can see that this is going to give you exactly p minus 1 times 2 times p. So, then this going to tell you that cosine square theta 1 is just half times 1 minus p. And similarly, you can check cosine square theta 2 again, because of the symmetry, this has to be exactly 1 by 2 times 1 by 1 minus 1 by q. And similarly, again using the symmetry, you can see that cosine square theta 3 will be half times 1 minus 1 by r. So, now the sum of this must be less than 1. So, that means half times 1 minus 1 by p plus 1 minus 1 by q plus 1 minus 1 by r is less than 1, and this implies 1 must be strictly greater than less than 1 by p, 1 by q plus 1 by r. Now, note that all this p, q, r, they are all positive numbers, okay, that is coming from this graph. So, now since there is this particular branch is there, you can see that p, q, r must be at least 2, okay, p, q, r must be at least 2. So, because of symmetries, we can arrange them so that p greater than or equal to q, q greater than or equal to r. So, without loss of generality, we can assume this. So, in particularly, you can see that 1 by p will be less than or equal to 1 by q less than or equal to 1 by r. Now, use this inequality in this inequality, then we get exactly. So, this is 1 by r is going to be less than or equal to 1 by 2, because r is at least 2. So, then using this, you see that 3 by r must be less than or equal to 3 by 2. So, which is greater than 1. So, that implies immediately r is less than 3, and since r is greater than or equal to 2. So, you get exactly r equal to 2. So, this puts lots of restriction and we get r is exactly 2. So, now use this again, and then if you go back to this inequality, you can see if r is 2, then 1 plus p plus 1 by q should be greater than 1 by 2. So, now again you can see that because q is greater than or equal to 2. So, now if you just use this inequality, you can see that this is greater than or equal to 2 by q. So, this implies 2 by q is greater than 1 by 2, then that implies 4 is greater than q, and already q is greater than or equal to 2. So, there are two possibilities. Now, in case q is 3, so this is the case 1, let us say q is 3 and r is already 2. So, then that forces that 1 by p is greater than or equal to 1 by p is strictly greater than 1 by 6. Then that will force that 5 is greater than or equal to p. So, then you have only following options, because q is at least 3. So, p must be greater than or equal to q, which is greater than or equal to r. So, that means p must be at least 3 and then at most 5. So, then you can see that the possibilities are 5, 3, 2 and then 4, 3, 2 and then 3, 3, 2. And then it is not hard to see, in this possibility you get E8 and then in this possibility you get E7 and then in these possibilities you get E6. So, in this q equal to 3 and r equal to 2, we get all types capital E. So, now let us see what happens if q is 2. So, q is 2, so then r is also 2. So, in this case you can go back to your inequality and then see that 1 by p plus 1 will be greater than 1. So, that means 1 by p is just greater than 0, but that is true for any p. Okay. So, again p has to be at least 2. So, that is the only condition. So, that implies you can have p to 2 where p is greater than or equal to arbitrary. And what is this case? This case just okay. So, this way you can see that we have lots of restriction for the Coxeter graph of admissible sets. So, now it is not hard to see how to use this for our root system. So, you can take pi to be a base inside your root system. Then what you do, you consider this pi tilde, which is alpha divided by norm alpha, where alpha comes from pi. So, then it is clear to see that this is actually just admissible set. So, then the Coxeter graph of this pi tilde is same as Coxeter graph of pi. So, now we already proved. So, the Coxeter graph of pi tilde has only the restrictions a g2 and then b, which is same as c, and then d e f. So, these are all the only possibilities. So, now by putting arrow you can see that the possibilities that we have listed are the only possibilities of Dinkin diagram of this pi. Okay. So, this completes the proof of the classification of irreducible root system. So, in terms of the Dinkin diagram. So, but later what we will do for each Dinkin diagram that is listed in the classification. So, we actually produce very explicitly root system corresponding to the Dinkin diagram. Okay. So, that I will do in the next class. So, I will just show you the classification, the table. Okay. I will end with that. So, here is the possibilities. So, you have this type A, which is simply laced, and then you have this type B and type C. So, which are actually dual to each other and they are not isomorphic. Okay. And then you have this type D, so which is again simply laced, which is self dual, and then you have this type E6, E7 and E8. So, and all this you can see that E6 naturally embedded inside E7 and then it is naturally embedded E8. In particularly, if you know what is the root system E8, in practice you will be able to get what is the root system E6 and E7 by ignoring like the corresponding combination of that simple roots that you have for 8. For example, if you ignore 8 you will get E7, if you ignore 7 and 8 you will get E6. Okay. And then you have this F4 and G2 and both of them are self dual. Okay. So, this is actually one of the biggest theorem that proved in last century. Okay. So, this kind of completes the picture of classification of irreducible root system, in particularly the classification of root system. So, we will see in the coming classes how to use this classification to get the classification of semi-simple Lie algebras. So, I already lectured many hours, around 30 hours. Okay. I do not have much more hours left. Okay. So, maybe we will not get into the too much details to go from the root system to the Lie algebra. Okay. We already saw how to go from the Lie algebra to the root system. So, the other way is again possible. We will do something, but for example, I will not prove the conjugacy of Cartan subalgebras. I will tell you like how once you assume conjugacy, how it helps to actually determine the root system uniquely. Okay. So, and then I will actually tell you like I will tell you everything about how to go from root system to Lie algebras. So, that way actually we complete the classification of semi-simple Lie algebras. Okay. I will stop here, we are running out of time. Thanks.